Okay, so we finally have a capable agentic coding model that you can run locally. This is Laguna S2.1 from Poolside. It's a 118 billion coding model that is comparable to models 10x its size. The best part, you can run it on DGX Spark at 80 tokens per second with speculative decoding enabled. But there is a lot more to this model. They also released their own agentic coding harness called Pool. We're going to look at that in a minute because it's specifically designed for long horizon tasks. Now, we're going to talk about how this model is trained and what exactly is special about it, because there is a lot to cover here. Okay, so it's an 118 billion parameter MOE with 8 billion active parameters per token, with a context window of 1 million token. They not only release the weights as open weights, but they also release the full trajectories of the benchmark. So everybody can go and look at how exactly this model performs, which is kind of new. Now, in this video, we're going to look at how exactly this small model punches above its weights and how you can run this locally. Now, we're going to look at how this is trained in a minute, which is very interesting, but let's look at some benchmarks. This is specifically designed for agentic coding, and it shows up in the benchmarks. We're going to look at just only one of them, but I'll put a link to the blog post if you're interested in more. So on Terminal Bench 2.1, it scores 70%, which lags behind something like Kimi K3 and GPT 5.6. However, this is a pretty incredible model for its size. It outperforms models which are 10 to 15x larger. So it's not frontier level coding, but it's an extremely capable model when it comes to open models that you can actually run. Now, they talk a lot about the harness that they used for running these benchmarks because that plays a critical role on how the models actually perform. Okay, so how does a model this small get good? The short answer is post-training, specifically reinforcement learning. So poolside framing is that almost everything humanity has ever written down records the answer, not the thinking that got there. And they believe reinforcement learning can recover that thinking, which is a very interesting framing. So their idea is that instead of only feeding it text, you drop the model into environment, give it a task that it cannot solve yet, and then reward the runs that actually worked. So classical reinforcement learning, they built thousands of different environments on real software engineering tasks. Now, this is pretty common. However, in this case, the reinforcement was learned in FP8 precision, which is lower precision number format that makes the training cheaper at this scale. So this is trained on almost 4,000 NVIDIA H200 GPUs, but the whole end-to-end training from pre-training all the way to post-training and RL was done under 9 weeks. And then, as like other models, it also self-optimized the harness around it. Now, this is a trend that we're seeing, which is good news. But the trouble is what the model will do to get its reward. Okay, so we need to look at well-known failure modes when it comes to reinforcement learning. The model optimizes the reward signal, not your intention. So if there is a shortcut that scores points without solving the task, it will find that. This is what reward hacking looks like. Now, the interesting thing is that they actually saw it. And so on SWE-bench tasks, they saw that reward hacking spiked above 50%, which essentially means that the model was gaming its own score. So they had an external LLM as a judge, which was looking at the full trajectory of what the agent was doing, and then they calibrated the judge against human labeled runs, so it lined up with how people would score it. Now, there were two other things. They did a prompt amendment, which basically told the model what not to do, and then a network blocked sandboxes, so it couldn't reach out and fetch the answer from somewhere else. We have seen an example of this. An undisclosed OpenAI model tried to find the answer, got into Hugging Face infrastructure and hacked the infrastructure in order to get the answer. So they're really training towards a behavior where they encourage the model for more verification, taking things less for granted, and also trying to encourage the model not to declare victory early. And this actually shows up. So if you run this model, it takes a lot of time during its reasoning process to verify what it actually is generating. Now, this is kind of unusual for an open weight model of its class. Okay, now let's talk about how to run this model locally. So it's a mixture of expert or MOE, which is great for devices like DGX Spark, because I think they are specifically designed for the MOE architecture. Because to generate tokens, the model reads the weight it needs out of the memory. In this MOE case, that is only the 8.5 billion, not the full 118 billion parameters. So the speed of generation really matters on the number of active parameters, not the total. Okay, but when it comes to generation speed, there are two different things to consider. One is the capacity, which basically determines how big of a model you can actually hold in memory. And then bandwidth is how fast you can read it back. So generating tokens one at a time is essentially bandwidth bound. So this is where exactly DGX Spark fits. It has 128 gigabytes of unified memory. So the CPU and GPU is essentially sharing that one pool, and the whole model lives in it all at once. On the bandwidth side, it's more modest, around 273 gigabytes a second, which is about 1 petaflop of FP4 compute. Now the thing is that this bandwidth would be painful for a dense 118 billion parameter model. But since we are only pulling 8 billion active parameters per token, so a small active count is actually pretty suitable for something like DGX Spark. Now, the catch is that those 818 billion parameters still have to be physically fit inside that 128 gigabytes. This is where the next problem comes in. So if you look at the full 118 billion parameters in full precision, that would be hundreds of gigabytes, way too big for 128 that we have on DGX Spark. So we need to quantize them. Now, the best part is that they natively ship it in NVFP4, which is a 4-bit quantization instead of 16-bit. Right, so you essentially need about 70 gigabytes for this to fit, which is great because now the DGX Spark 128 gigabytes actually fits everything with enough headroom both for context and KV cache. Also, DGX Spark natively supports NVFP4, so you can actually use it. But even natively at these bandwidths, the generation speed is still slow. So let me show you the trick that fixes that generation speed. Okay, so naively, if you are doing one token generation at a time, you will need to pass through the whole network for every token that is being generated. On DGX Spark, that lands around 12 to 15 tokens a second. It's usable, but a little slow. And the reason is that it's the decode is memory bound and you pay the full weight read for every token. Now, the trick is decoding. So you bring in a small fast draft model that guesses several tokens ahead, and it's pretty cheap. Then the big model simply checks the whole guess in one pass. Here it's up to 15 tokens a time and simply keeps the one that it agrees with. So you're still getting the exact output from the big model. You just verify in blocks instead of looking at it one token at a time. Now, Poolside's drafter is based on a DFlash. It is essentially a block diffusion speculator, which is a small 5-layer model in the Llama style. And the good part is that it actually shipped that draft checkpoint with the model itself. Now, if you want to learn more about speculative decoding, I actually created a couple of videos on those, specifically the DSpark speculative decoding method from DeepSeek. Okay, so how fast you can get with speculative decoding on DGX Spark? The reported numbers from community is 76 tokens per second with a peak of 117 tokens. On my DGX Spark, thanks to NVIDIA, the maximum I got was 84 tokens per second on a single thread. Now I'm running more experiments. By the time this video is released, I will put together the numbers. But with the speculative decoding, you can actually get substantial speed improvements compared to without it. Okay, now with this model release, they also released their own agentic coding harness. This is called Pool. So the experiments that I wanted to run was with the agent harness that they're creating natively with the model, and I wanted to see how good this is. And it's actually, I think, a really well-designed harness. Okay, so I installed it on my local machine. The model itself is running on the DGX Spark that I have. Now in here, it is very similar to the modern agent harnesses that we have seen from other companies. For example, you can select a model. At the moment, there is only Laguna S21. This is the only model that is running. I think you can potentially bring other models as well, but this is a relatively leaner harness. Now, this is the harness that they are using process. So all of the benchmarks are actually through their harness. So that's a very important thing to keep in mind when you are running this model. Now, to test this, I ran this simple prompt where I asked it to create an HTML file that has information about Pokemons, including their animation and stats in a self-contained HTML file. And it does a pretty good job at this. Now, the most important thing is that the thinking and reasoning process is very elaborate. It does spend a lot of time thinking about the problem that it's trying to solve. Now, here's the final output, and it does actually a really, really good job, right? So it has all the different Pokemons with their animations. Most of them are pixelated, right? And if you click on this, it basically gives you the base stats, height, weight information, right? It's surprisingly well. I wasn't expecting something like this from an 8 billion active parameter model in NVFP4, but the model is surprisingly good for agentic coding. Now, another interesting aspect of this model is that the chain of thought is extremely verbose. So for example, if we ask for something like this, right now it's actually thinking through all of its steps. Now, there are multiple different threads running in parallel. I wanted to see how far we can push it in terms of concurrent sessions. But you can see it basically think through about what it's going to implement pretty rigorously. Also, as I pointed out before, during the chain of thought, seems like it doesn't really differentiate the chain of thought from the actual response, at least in this harness. This could be an issue related to the harness. Okay, so it is kind of stuck in a loop, and it seems like it's just overthinking. So for example, here it says, okay, I think I have planned enough. Let me write the actual code. Then it thinks about, okay, let me write the code now. I'll aim for something that's both impressive and performant. Then again, it says, okay, I think I have planned enough. Let me write the code, right? One more thing. I need to handle the window resizing, right? And this is probably coming from the quantization, because there is actual research which shows that quantizing MOE make them think for a lot longer. And we actually see that effect right here. Okay, so here's the paper I was referring to. Quantized reasoning models think they need to think longer, but they do not. If you're interested, let me know and I'll create another video breaking it down. But it's a very interesting piece of research. Okay, so that version is still running, but here's a version that was created by a previous iteration. Now, for some reason, the voxel garden is upside down, which is first, and then the trees are coming out on the other side as well, right? But this in itself is a pretty complex prompt, and you can actually change it to night mode. Now, in general, for a effectively 8 billion parameter model, I think this is pretty decent. The model definitely has capability, but I think it probably need better prompting and maybe higher quantization. Anyways, do check it out. It looks like a very interesting model that you can run on something like DGX Spark easily. The more exciting part is that we're seeing a lot of open weight models now, even from Western labs, which is really encouraging. Anyways, I hope you found this video useful. Thanks for watching, and as always, see you in the next one.